If you remember, in the previous video, we used the gated method for a woofer. The issue is that the measurement range was incomplete and needs to be extended. Watch the previous tutorial to learn how to perform the gated measurement. Before diving into the next part, here are a few things to keep in mind about gated measurements. Some methods use a speaker on a spinning plate, which can be made with a stepper motor and an electronic board. You can define the desired number of steps for it, but the key is not to design something complicated, it's to perform a precise measurement that can be done manually with simple tools. If you know the number of steps, the measurements are automatically named using this method. Increment means how much the speaker will rotate in degrees with each step. For VituixCAD software, the naming format is After measuring, set it at % to have a clear impulse. To extend the response, place the microphone as close as possible to the speaker. It's better to limit the range for bass measurement. I select it between 20 and 600. My driver is mounted on a sealed box. If you have a ported one, you need to measure its response separately. And if it's a sealed box, only save the driver response. Now import the bass response into this tool of the VituixCAD software. Export this file and compare it with the previous one on REW. Just drag it. The result on the baffle is 6 dB below the previous one. Now, we need to apply the bass on all the measurements. Do it like this. Create a subfolder and choose a name for it. For example, merged. We need to import one bass response and all the measurements here. After that, equalize the bass response to all the others, which can be done with the down arrow key. The starting point of the measurements is 250 Hz, and the bass response covers 20 to 600. 300 Hz is a good value to overlap the bass and the other responses. Be sure that you check this box and save the new files in the merged folder. Congratulations, you did it correctly, and the bass has been added to all the responses. If you drag the new responses into REW, the result is Next, we should analyze the speaker's behavior in VituixCAD. One key aspect to consider is the significant sound pressure emitted from the rear side of the driver. This rear radiation interacts with the room, creating reflections that can negatively impact the listening experience. These reflections introduce sound that is out of phase with the direct output of the driver, leading to a less accurate and less enjoyable sound. At higher frequencies, the rear radiation becomes significantly weaker, and the sound becomes more directional, closely resembling the driver's original response. However, for an optimal listening experience, the directivity plot should exhibit a uniform shape. This is best visualized on a contour plot, which highlights how consistently the sound is distributed across different angles. As you can see, my speaker's directivity plot shows that directivity starts to take shape above 2000 Hz. On the plot, the vertical scale on the right represents the angles, while the one on the left shows SPL in dB. Notice that after 3000 Hz, the sound pressure drops sharply beyond 90 degrees. Ideally, we aim for a uniform response across all frequencies. Take a look at the smooth, consistent results here. There are several tips to improve directivity. You can use horns, electronic or active directivity control, or passive directivity control methods. Passive techniques often involve the use of acoustic materials, or creating acoustic delays to shape the sound field more effectively. Thanks for watching this video. Don't forget to try your own measurements and share your findings in the comments below.